Our roadmap for today. First, we'll map out structural isomers. Then, we'll look at the magic of tautomerism, followed by twisting bonds in conformational isomers. After that, we'll navigate cycloalkane rings, look at locked forms in geometrical isomers, and finally, master easy nomenclature. Let's get right into it.
Section 1. Mapping structural isomers. These are basically the Lego bricks of chemistry.
So, structural isomers. These are molecules that share the exact same molecular formula, but they feature entirely different atomic organizations. It's kind of like having the exact same pile of Lego bricks, but building completely different houses out of them. To figure them out, we use something called the degree of unsaturation. It's this super handy mathematical diagnostic that instantly reveals hidden double bonds or closed loops in the structure. It's absolutely crucial to do this first before building out any molecular architecture. And why does this matter? Well, because these different structural foundations completely dictate how a molecule interacts with your body and the physical world around us.
Just take a look at chain and positional isomers. Pentane, for example, forms a simple straight line, while isopentane branches out, right? That completely alters its physical shape. Then functional isomerism and metamerism take it even further. It's wild. The exact same atoms can assemble into an ether, or they can completely change their chemical identity to become an alcohol. It's a total shift in behavior, all from the same starting ingredients.
Moving on to Section 2, the magic of tautomerism, or as I like to call it, molecular shapeshifting.
Imagine a building that's just constantly rearranging its own windows and doors. That raises a really fascinating question. What if a molecule can spontaneously change its own internal structure back and forth? Well, that is tautomerism. Notice the dynamic equilibrium going on here. You've got a keto form with a carbon-oxygen double bond, and it rapidly flips into an enol form, where that double bond actually shifts over to create an alcohol group. The whole trigger for this incredible shape-shifting? It's just one sneaky alpha hydrogen that migrates, setting the entire rearrangement into motion. Now, there is a really dramatic exception to this, and that's phenol. See, while the keto form is the comfortable default state for most molecules, phenol actually prefers the enol form 99.9% of the time. Why? Because shifting into this enol form creates a continuous, highly stable aromatic ring. The molecule is smart, you know? It naturally defaults to the path of maximum stability.
All right, Section 3, Twisting Bonds. Let's talk about conformational isomers.
Conformational isomerism is all about the infinite number of 3D spatial arrangements a molecule can take. Because remember, single carbon-carbon bonds act exactly like axles. The attached atoms aren't permanently locked in place. They continuously rotate, twist, and writhe, constantly seeking the lowest possible energy state. Chemists actually visualize this using what we call angled sawhorse and head-on Newman projections. If you look straight down that carbon-carbon axle in a Newman projection, you see the staggered form. This form keeps those bulky groups spread out to minimize steric strain. Basically, they want their personal space. Conversely, the eclipsed form forces atoms to line up right behind one another. As you can imagine, that is uncomfortably crowded, drastically increasing the molecule's energy and instability. So, there's a strict hierarchy of stability here. Think of the anti-conformation, where the bulkiest groups are exactly 180 degrees apart, as a deeply relaxing stretch. It boasts the highest stability and the absolute lowest torsional strain. The Gotch form? That's somewhere in the middle. And then the eclipsed form suffers from the highest strain. Because of this, molecules naturally spend the vast majority of their time just chilling in that comfortable anti-position.
Next up, Section 4, Navigating Cycloalkane Rings. Welcome to the Lord of the Rings.
Okay, so when carbons form rings, forcing them tighter than their preferred 109.5-degree angle causes some severe angle strain. That tiny 3-carbon ring, it is incredibly tense and highly reactive. Stability does improve as we move to 4 and 5-carbon rings, but the 6-carbon ring, cyclohexane, that one reigns supreme in chemical stability. But here's the catch. It doesn't achieve this by staying flat.
To relax, that 6-carbon ring actually puckers out of a flat 2D plane and forms this 3D chair conformation, totally minimizing the strain. Notice the bonds here. The axial bonds point straight up and down, while the equatorial bonds point outwards. For maximum efficiency, the molecule cleverly positions its large, bulky groups on those outward-facing equatorial bonds to avoid clashing. This kind of molecular ergonomics is absolutely crucial when we're designing stable, effective pharmaceuticals. Section 5. Locked forms.
Let's dive into geometrical isomerism.
This brings us to geometrical isomerism. The rules change here. When you add a double bond or a rigid ring structure, the molecule can no longer twist freely. That axial is completely frozen. This locks the attached atoms into permanent, unyielding spatial positions relative to one another.
Because that central double bond absolutely cannot rotate, two distinct setups naturally emerge. The cis form locks matching priority groups on the exact same side. The trans form? That locks them diagonally opposite. And this seemingly simple spatial difference is a real game changer. It fundamentally alters the molecule's melting points, boiling points, and its entire set of chemical properties.
Finally, Section 6, Mastering Easy Nomenclature. Now, when molecules have four completely different groups attached to a double bond, terms like same side or opposite side kind of lose their meaning. So to solve this, chemists use the CIP priority rules. That's Kohn-Ingold-Prelog. It's a highly organized system that determines the exact 3D configuration, labeling it as either E or Z.
All right, let's break this down into an actionable checklist. Step 1. Look directly at the atoms attached to the locked carbons and rank them by their atomic number. Step 2. If there's a tie, simply walk down the chain to the next atom until that tie breaks. And Step 3. Treat any double or triple bonds you hit as multiple single bonds to that atom. Follow these, and you can sort out any structure.
Let's actually put this into practice. Looking at the atoms directly attached to the central carbons, we assign priority 1 to the highest atomic number. Notice how a much heavier halogen, like iodine, instantly outranks bromine, and bromine outranks your standard carbon groups. This step definitively sets our high and low priority lanes on both sides of that double bond. Tying the whole shebang together, we just look at where those number 1 priorities landed. If the top priority groups are locked on the same side, it's Z for zusammen, which is German for together. If they are diagonally opposite, it's E for entgegen, or opposite. It is beautifully logical, giving us a complete microscopic sorting system.
So we've journeyed from flat atomic formulas into a dynamic 3D universe where molecules shift, fold, and lock into the rigid geometries that literally define the fabric of our reality. It's truly incredible to realize that the rules governing our whole world operate on this hidden architectural level. If you can decode these 3D molecular blueprints, what other invisible architectures of our universe are waiting for you to uncover? Keep exploring, and I'll catch you in the next explainer.